Recording in progress.
In last video, we discussed matrix arithmetic. In this video, we'll talk about linear subspaces and study some linear subspaces which are naturally associated to a matrix or linear transformation. Definition: a subset V of Rn is a linear subspace if it contains vector 0 and all linear combinations of its elements. That is, if V1, V2, and so on, Vn are any collection of vectors in the subset V, and C1 through Cn are the scalars, then the linear combination of vectors C1 V1 plus C2 V2 plus etc. plus Cn Vn is in V. An equivalent formulation: for every two vectors V and W in V, and scalars C and D, the vector CV plus DW is inside V. After all, the expression C1 V1 plus C2 V2 plus etc. plus Cn Vn can be computed by adding only two vectors at a time. Some trivial examples. The subset 0 inside Rn is a linear subspace. Any linear combination of zeros is again 0, so hence it's a subset. Subset, well, Rn as a subset of itself is a linear subspace because it contains 0 vector, and any linear combination of vectors in Rn is some vector in Rn. Linear subspaces of R. The only linear subspaces of R are 0 and R itself. Let's see how it works. If V inside R is a linear subspace and little v is a non-zero vector in capital V, then any W inside R in R can be written like this. Right, so we can divide by V and multiply by V. Hence, it's a multiple of V. Since big V is linear and contains little v, it must also contain W. So that proves the statement. Now, let's talk about linear subspaces of R2. Any line through the origin in R2 is a linear subspace. Why? Well, it contains 0. And recall the geometric rule for adding vectors, right? So any sum of vectors on a line remains on a line. So these two vectors, AB and BC, add up to vector AC. Okay, let's see if you understood the concept. Is this a linear subspace of R2? The origin? Yes, it is. The x-axis. Yes, right, because it's a line that passes through the origin. The y-axis. It is the union of x-axis and the y-axis. No, it's not, right? Because the linear combination of vectors can leave you, will get you outside of the set, right? So if you take a vector on the y-axis and add it to the vector on x-axis, you're not going to get a vector outside of this. Is this a linear subspace of R2? Another example, the hyperbola xy equals 1. Well, it's not because it does not contain a 0. The graph y equals 5x. Yes, it is because it contains the origin and passes through. It's a line that passes through the origin. Graph of y equals 5x plus 3. It is not because it does not contain 0. Sin x, it's not a line. Okay, some more. The circle. No, right, because it's not a line, doesn't pass through the origin. This circle that that passes through the origin. Also no, because it's not a line. All R2 except the origin. Also negative, it must contain the origin. And all of R2 is, it is, right, by more or less by construction. Okay, some more examples. Yeah. So say V is a linear subspace of R2. If V contains a non-zero vector, then it must contain the linear span of that vector. That is the line that passes through it. If V contains any two vectors not on the same line through the origin, then since these vectors span V must contain all of R2. So V must be 0, a line through the origin, or R2. So this is the classification of linear subspaces in R2. Okay, now let's move on to R3. Any plane through the origin in R3 is a linear subspace. It contains 0, and then, well, if you draw any two vectors that are on this plane, like V and U, so every two vectors that give you a plane, then their sum will remain in that plane. So any linear combination of that vectors, in fact, will do. So any linear subspace in R3 is the origin, 0 vector, a line or plane to the origin, and the R3 itself. Indeed, so any non-zero vector spans a line. Two non-collinear vectors span a plane. Non-collinear means non-parallel, so we can bring them to the same point, to the same origin. And three non-coplanar vectors span all of R3. Linear spans. The linear span of any collection of vectors is a linear subspace. Let's prove it. Consider vectors v1 to vn, and then take W to be the linear combination of these vectors with coefficients ai, and x be the linear combination with coefficients bi. Then any linear combination of W and X will look like this. And using rules of simple rules of arithmetic or vector arithmetic, you can make this calculation. So on the right hand side, you see that it's again a linear combination of the same vectors in the I. Now let's talk about ranges. The range of a linear transformation is a linear subspace. Take two vectors v and v prime, which are in a range of transformation T, which means that there are some W and W prime with the T of W equals V and T of W prime equals V prime. Thus, any linear combination of these two vectors, again, using rules of, using the fact that T is a linear transformation, we can conclude that this linear combination is contained in the range of T. Column space, if A is the matrix of the linear transformation T, the range of T is the span of the columns of A. We call this column space of A. So you remember, we take those vectors E1 through En, which look like 1, 0, 0, 0, 0, 1, 0, 0, and so on. So these columns are T of E1 and so on, T of En. So for any W in this range, V is equal to T of W. And we can write that W is equal to the sum Ci EI, and hence V is equal to T of W equals Ci times T of EI. Let's look at an example of a column space. In this reduced echelon matrix, what is the column space? is the set of vectors with zeros in non-pivot rows. It's spanned by the and it's spanned by the pivot columns. So and the same is true for an echelon matrix. And here, yes, in this reduced echelon matrix, yes, it's the same is true for the echelon matrix. Next, a null space. The set of vectors sent to 0 by linear transformation is a linear subspace. So null space is also a linear subspace. Indeed, so T of V equals 0 and T of W equals 0. Then T of CV plus DW is equal to C times T of V plus D T of W, and then it's equal to 0 because each of those vectors is equal to 0. And this is called the null space of the linear transformation, or of the corresponding matrix of this linear transformation. Basis, definition. A basis of a linear subspace V is a collection of linearly independent vectors which span V. As an example, the empty set is the basis of the vector space 0. Vectors 1, 0, 0, 1 give a basis of R2. Vectors E1, E2, and so on, En give basis for Rn. In a reduced echelon matrix, we already saw the pivot columns span the column space. Since they are distinct vectors EI, they're linearly independent, so hence they give a basis. So if you look at them, pivot columns look exactly like this. Let's prove a theorem. Any linear subspace V of Rn has a finite basis. So it means this has finitely many vectors that form a basis. So there's a constructive proof. Begin with the empty set of vectors, then enter the following loop. If the current set of vectors spans V, then stop. We are done. Right? Otherwise, take any vector in V that do not span the current set and add it to the set. So you would start, say, with taking the first vector. And then you just do it, and then you do it over and over again until you have completed until the set of those vectors span the entire span Rn. So to see that this procedure gives a basis, note first that the set of vectors being built is always linearly independent. At each step, we add a vector not in the linear span of the other vectors. From this, we conclude that the procedure must terminate because every linearly independent vector subset of Rn has at most n elements. The procedure only terminates once the A spanning set for V is found. Thus, every linear subspace of Rn has a basis. If we begin with the finite spanning set V1 through Vk for V, for capital V, then the following variant gives an actual algorithm. In order to find the basis, so begin with an empty set of vectors and then enter the following loop. If the current set spans V, then we're done. Otherwise, we take the lowest indexed vector among those VIs, not in the span of the current set, and add it to the set. So to see that if V n plus 1 is in the span of V1 through Vn, we can form this augmented matrix with a V1 through Vn on the left and then Vn plus 1 in the right-hand side. And solves the corresponding systems by row reduction. In other words, if we need to understand if this vector Vn plus 1 can be presented as a linear combination vectors v1 through vn. Instead of doing this each time, you want to check linear dependence among some of the VIs. We can do it all at once, right? So a linear dependence between the columns v1 to vn is by definition is the expression of the form sum xi vi is equal to 0 for some coefficients xi, which in turn is an equation mx is equal to 0. So now the way it works in practice is the following. So a sequence of row operations is performed by multiplying m on the left by a sequence of elementary matrices. First, it's E1, E2, and so on, En. Or we can write this, abbreviate this to be equal to R. Right? It's the product of E1, E2, and so on, En. We need to remember, you need to read that right to left. So simply M goes to R, M goes to Rm. Now, since R is invertible, Rmx is equal to 0 if and only if Mx is equal to 0. And therefore, row operations preserve linear dependencies between the columns. In a reduced echelon matrix, a basis of the column space is given by the columns with pivots, as we discussed before. Thus, in any matrix, a basis for the column space is given by the columns which will have the pivots after row reduction. And then we need to make sure that we use the columns of the original matrix, like we don't swap them around. So let's take an example. Find the basis of the space spanned by these vectors, these 5 vectors with 4 components each. So clearly some of them will be redundant, right? Because so we expect 4 vectors to be a basis in 4-dimensional space. So the first step is to put them in the columns of a matrix like this. So we'll keep the same order. And now row reduce it. So this is the standard procedure. You know how to do it. The first step, second step, third step. So that's the row reduce matrix. So this final matrix has pivots in first, third, and fifth columns. Thus, the first, third, and fifth columns of the original matrix form a basis of its column space. Right, so we can just dial back those elementary transformations. Yeah, and then they form the basis in the subspace of these 5 vectors, right? So the other 2 vectors can be expressed as a linear combinations of these 3. Now let's find the basis for the null space. So we can also, so if consider the null space of matrix A. In other words, the basis for the space of solutions to this homogeneous equation AX equals 0. And in fact, we already know how to do this, right? So we do the augmented matrix with 0 on the right-hand side, and then we just read off the answer. So how to find the basis for null space of this matrix? Well, we do the row reduction. With augmented matrix, we'll have with zeros in the rightmost column. So after completing the steps, we'll get to this matrix over here, which we just did. Now, the row reduction does not change the space of solutions, so we read them off the reduced echelon matrix. And we introduce the 3 parameters for the non-pivot columns, including the last one, right? So here the 3 parameters for the non-pivot columns, not including the last one. So S and T for columns 2 and 4, right? And we can read off the answer so that the So x5 is equal to 0, x4 is equal to t, x3 is equal to negative t, x2 is equal to s, x1 is equal to negative 2s minus t. Or in other words, we can write it like this. So in other words, a basis for the null space is given by these two vectors. With this coordinates.